With this configuration, we hope to have an output that scales the difference between the two inputs, or even better, we hope to have an output that scales individually each input and then performs the difference operation between them. Alright, let's analyze this circuit. I know that the output is going to be V plus minus V minus over times A0, and our goal here is now to eliminate this V plus and V minus from our equation here, so we can have familiar terms here and see what we got. I will notice that there is a current flowing from the input to V2 all the way to here, and then it flows all the way to the ground. It can really flow inside the op-amp, which tells me that this whole thing is nothing but a voltage divider, with the voltage here V plus being equal to the total voltage of between these two resistors, alright, V2, times the total resistance being tied between V plus and the ground, Rg, over the whole total of resistance between V2 and the ground, which is R2 and plus Rg. Alright, if there was some leakage current flowing inside the op-amp, where the op-amp was not ideal, we would not have a voltage divider here. It's important. We can say this because the current is common. Now I call this current I1, which is the current that flows from the input V1 all the way to here. It can't flow inside the input of the op-amp, and it flows all the way to here. Alright? By the way, this current is going to go all the way to here and all the way to here. Where will it flow then? Inside the op-amp. It cannot really flow inside the output. Alright? Remember that the ideal op-amp does not allow a current to flow inside the inputs, but it has an infinite current source here that can draw infinite current or can create infinite current, let's say. Alright, now if I perform Ohm's law here, R1, it's going to tell me that, well, R1 must be equal to V1 minus V minus over I1. And if I do the same for the resistance of RF, I'm going to say that RF also is V minus V out over I1. Obviously, the polarities are here for the resistances, right? Are like this. But the resistances are symmetrical devices. They do not have a polarity, but it's good for us to be vigilant with the polarities of any device that we are going to see in our circuits, because if we take into account this, we can avoid lots of mistakes. All right, now I can say, well, this I1 and this I1 are the same again, and I can safely say that V1 minus V minus over R1 is equal to V minus V out over RF. And if I do the math here and solve in respect to V minus, I get this whole thing here. And that's it. Seems to me that I've solved in respect to V plus, I've solved in respect to V minus, and I have known quantities both here and here. Now I go back to my equation 1 and I replace these two values with the ones I know. Alright, in my equation now I have V2, V1 and V out here, and if I try to separate these terms, I get my beautiful result here. The output is something times the input V2 minus something times the input V1. And that's, again, thank God, the same as I wanted in the beginning. The output is a scaling factor of V2 minus the scaling factor of K1 times V in 1. All right? And I have absolute control over these two values. I can set the resistances as much as I want with whichever gain I have here. I might have an infinite gain. I might not have an infinite gain. Whichever case is true, I have a general solution here for everything. Now let's make some observations. Well, say, what if these resistors R1 and these resistors R2 are the same, and so is RF and RG? All right, I named this RF because it's the feedback, and RG because it goes to the ground. And what if the gain is infinite in an ideal op-amp situation? Well, in that case, I have an output that is a scaling factor times V2 minus V1, K times V in 2 minus V in 1, as I wanted from the beginning. Now, what if, well, these are the same and A0 is not very large? Well, in that case, if I do the math here, I get this output. Again, same as this, but I have also a factor of A0, 1 over A0 here, which I will also have to take into account. All right, we did not have this here because A0, if it's infinite, this term becomes 0. This term simplifies with this term, and I have RF over R1. All right. And now I'm ready to solve an exercise that tests my knowledge. I write the general equation here and the circuit here, and I'm given an op-amp of A0 of 40, and I'm asked to build an amplifier that performs this mathematical operation. Then I notice the scaling factor of the two signals and a minus sign here, which prompts me to perform a difference. Now, if I say, well, what if RF is 100 ohms, right? That's a logical value. No particular reason I chose this. And I take one of the two terms. I'll pick this term because it has the less number of unknowns. Notice it has two unknowns here, RF and R1. This term has 4 different unknowns. I pick this term, and I'll say if RF is 100 ohms, and I replace all values here, RF with 100 and A0 with 40, and I say this whole thing is equal to, all right, minus V1. I'll say Y is the V1 signal. I get that R1 must be equal to 2.44 ohms. Very logical result. I can buy this resistor, and if I can't, I can create this resistance by adding some resistors in series or in parallel very, very easily and very cheaply. All right, this term seems to be created very, very easily. And now I'm going to solve for this term. Now I'm going to say that, all right, I have two terms here, R1 and RF, and I have another two. Well, I'll pick RG, no particular reason, and I'll say, what if RG is 100 ohms? All right, no real reason I choose this value, just a logical value of a resistance I can buy very, very easily. Now I replace all values here and say this whole thing must be equal to 10, and then I have only R2 as an unknown. And if I solve for R2, I get this result. R2 must be equal to 104.1 ohms. Again, I can build this very, very easily. I can buy a 100 ohms resistor and a 4 ohms resistor and a 0.1 ohm resistor, and I put them in series, all right, or many other ways. Very, very, very easily and logically, I have created configuration that performs this mathematical operation. Alright, the gain is not very large, it's a gain of 40, and with very small resistances, alright, and very cheaply, I have performed my operation here. And that's it. That was the differential op-amp. If you have any questions, write me down in the comments below and subscribe to the channel for more electronics videos. Study well and take care.